Do we want to get started? All right, let's go ahead and get started. My name is Anthony Liguori. I'm a senior principal engineer within EC2, and I've led the development of the Nitro system. Over the last year, I've also led the engineering effort behind Firecracker, which we just announced earlier this week, and most recently, AWS Outposts, which we just launched today. So really exciting week. I'm super excited to share all of the exciting things that we're doing with all of you. And I really appreciate you coming to a 7 p.m. meeting toward the end of this event. I know I'm standing between everybody and beer and food, so I appreciate you taking the time to come and listen to what I have to say. We're going to start out with an overview of what Nitro is, why it matters, and how it works. Last year, I did another presentation on Nitro, and we kind of scratched the surface. This year, I want to go really deep in a specific component, and that is the Nitro security chip. And so we'll talk a lot about why that exists, what it does, and what we use it for. Then I wanted to walk through some of our recent launches and talk about how Nitro enabled those launches and how it's providing benefits to you very concretely with some of our recent instance types. And then finally, I'll end with what's coming next. So what is the Nitro team working on? What are we looking towards in the future? The Nitro project began really with a question to ourselves. And that question was, after almost 10 years of having developed EC2, if we could take all of our learnings from that, and we could look at the physical hardware platform that we use to host EC2 instances, that we have very, very large number of these servers, and we questioned every single component in the system and said, is this the right component for the specific purpose that we're trying to meet here, which is to serve EC2 instances? And then from a software stack, to look at every piece of software in a system and say, do we really need to have systemd on every single server? The answer is no. Do we really need to have SSH and interactive logins? The answer is no. And we went through and we really tried to understand, since these servers only are used to run EC2, how could we really optimize them? This ultimately is what led to Nitro. And this is a platform that we launched with the C5 instance type in November of last year. And then we really started to talk about it reInvent last year. So it's just about 1 year old based on that. While this is really the first time we've started talking about Nitro, Nitro is a system that's been under development since at least 2013. When we launched the C3 instance type with enhanced networking, that was our very first use of Nitro hardware. Since we launched Nitro last year, every single instance type we've launched since then has been based on the Nitro system. So chances are, if you're using a C5, M5, R5, T3, any of the AMD-based instance types, if you got really excited like me and launched an A1 instance as soon as it became public, that's all based on the Nitro instance, or the Nitro system. So when we think about the Nitro system, and the reason we call it a system is it's really composed of 3 independent parts. The first part is the Nitro Card itself. This is the I/O accelerator within the system. And this year, one of the things I wanted to talk about is that this is actually not just a single card, but this is actually a family of cards, each that serve different purposes. And we'll talk about those cards a lot more in the next few slides. Security is the most important thing we do at AWS. It is part of every conversation we have. It's the first thing we think about when building anything. And so when we went to build Nitro, one of the big questions we asked ourselves was, could we do more from a security point of view? And that led to the Nitro security chip, which we'll talk a lot more about in a bit. And then finally, once we've done all of this, once we have all of our I/O offloaded, once we've simplified the stack, it led us to revisit what a hypervisor actually needed to be. And that led to the development of the Nitro hypervisor. The Nitro hypervisor is unlike any other hypervisor out there in that it does very, very little. And we'll talk about exactly what it does in a bit. I often like to refer to I/O in the world of virtualization as really the soul of a virtual machine. It's what gives it the personality, the type of block device you get, the type of network interface you get. that really is what defines your experience with that virtual machine. And so we'll start out by talking about what the Nitro Cards are and how they work. As I mentioned, there are multiple Nitro Cards. Today, there are 4 distinct Nitro Cards. There is the Nitro Card for VPC, the Nitro Card for EBS, the Nitro Card for instance storage, and then finally the Nitro Controller. All of these cards are actually physically different. And if you think about it, it makes a lot of sense. If you have a controller for instance storage, that controller needs to talk to NVMe devices behind it. It needs to talk to the host system. But if you have a Nitro card for VPC, it needs to talk to a network, right? So the type of physical hardware that you build is going to be different for those different use cases. However, these are all based on the same underlying ASIC. And we obviously share software where it makes sense. Something that we haven't really talked about in the past is the Nitro Controller. We'll talk a bit more about that, but it's really the brain of the system overall. It's what ties everything together and makes it cohesive. So let's deep dive into each of these types of cards. The Nitro card for VPC, if you could take it out of one of our servers and you could look at it and put it in a different server, what you would see is something to the OS that looked like a normal network adapter. Not that undifferent from something you'd get from any of the major vendors. The actual driver that would bind to it is the ENA driver, the Elastic Network Adapter driver. But this is a special network card in that it only works for VPC networking. It only works within the context of the Nitro system. So the Elastic Network Adapter is something we introduced a few years ago. And we introduced it to solve a problem that NICs tend to have. If you're running on bare metal in your own data center, you don't really think about the fact that if you have a server that was built for 1 gig networking, and then you upgrade that server to 10 gig networking, you're adding a different NIC, and then critically, you're usually installing different drivers. And it's very rare, in fact, I don't know any cases of this in practice, that you see a single driver that works across generations of the underlying network technologies. This isn't really a big problem when you're installing servers by hand locally, but if you're in a virtualized environment and you're using things like AMIs, this becomes very disruptive, right? You don't want to have to change your AMI. You don't want to have to change your application. It's far better if when we launch something new like C5N, you can just take the instances that you were previously running, relaunch them on that new instance type, and just get better networking. And that's really the experience we want customers to have. And so that led us to build the Elastic Network Adapter interface. Today, drivers are available for all major operating systems. For open source operating systems like Linux or FreeBSD or any of the other popular ones, those drivers are upstream today, so they come by default. They're shipped in all of the major distros. The other important component of the Nitro card for VPC is the actual VPC data plane. So this is the bit that actually allows your instance to talk to other instances within a VPC. VPC is a software-defined network, and so it's not surprising that we do encapsulation and decapsulation. But there's a number of other features that we implement within the Nitro card for VPC, such as security groups, limiters, routing, et cetera. Security groups are implemented in the card itself because we want to enforce those security groups as close to the origin of the data as possible. And this is one of the great things about the way security groups work within EC2 is that it doesn't rely on configuration within the instance. And because of the Nitro card, the same security groups happen on your platform, even if you're running bare metal where there's no hypervisor present. We can still implement that same level of security. A question that customers frequently ask is about limits in terms of how much performance a specific instance type can get. And one of the most important things that we focus on when it comes to performance, besides the actual raw performance, is making sure that customers can have a consistent experience when it comes to performance. We want to make sure that every C5 2x large, no matter which server it lands on, which region it's located in, which data center it's in, where it is on the network, always has the same performance experience. This is critical for distributed applications. You can't really rationalize about a distributed system if every node within that system is behaving slightly differently, or if one node can handle more traffic than another. You just simply can't scale that type of distributed system well. Now, often the question that we get asked is how many packets per second can a particular instance type handle? Unfortunately, it's not a simple answer. So not every packet is created equally in terms of how much it expenses the overall system. For instance, if you have a workload that is trying to send really large UDP packets and ultimately creating fragments, fragments tend to be expensive everywhere in the network. There's really just no easy way to handle fragmentation. Generally, you should try to avoid fragmentation, but people do it, and we certainly support it. On the other hand, if you have a very large TCP flow that is able to use the full MTU of the system, that's actually an easy packet to process. It's generally pretty straightforward. What we've done over time is that we've actually built a fairly sophisticated set of limiters that try to take all of these different equations into account to ensure that no matter what is happening, you're always getting the same consistent performance experience. So generally, the best advice that we can give to customers when it comes to limits is to take your application and actually try to push it to whatever is the maximum throughput it can achieve. And then we're always happy to have a conversation about whether we think that's an accurate characterization of what the system can do. Now, networking is super important for a lot of customers. A lot of their data flows through the network. But we also have a lot of customers who really depend on fast block storage. These are customers that are using things like relational databases or other types of workloads that expect to have block storage. And so the next card we built after the Nitro Card for VPC was the Nitro Card for EBS. And this is actually something we launched with the C4 instance type. It's been around for quite a while now. And even though this wasn't how we exposed it to customers, if you took that card, or if you take the current generation of that card, and you put it into a server, what you would see is an NVMe storage device. NVMe is actually a really exciting standard. It's relatively new, at least in terms of how storage works. And it's common. My laptop has NVMe. I suspect a lot of your laptops have NVMe. And unlike networking, the networking world, the storage world is a lot more standardized and a bit more forward-thinking. So NVMe likely will be able to last us through multiple generations of storage technology. Now, exposing NVMe is one part of what the Nitro Card for EBS does, but the obvious other part that's really important is taking that NVMe interface and turning that into network traffic. This has actually become pretty popular these days. You'll hear phrases like NVMF for NVMe over fabrics. There's a lot of different implementations of NVMe over fabrics, everything from TCP to Ethernet to RDMA and the like. But this is actually something we've been doing now for three or 4 years, is remoting NVMe, and it's worked out really well for us. Finally, the other capability and the other really important capability of the Nitro Card for EBS is volume encryption. So we rely on the Nitro Card to actually do the encryption of all of the data for encrypted volumes at the source of the traffic and using hardware-based encryption. So you never have to make a trade-off with Nitro for encrypting your data or getting the full performance out of the system, because that's all handled in hardware. Now, network storage is great. And for most customers, this is actually the right way of doing block storage. You get better durability, and you get the ability to do things like snapshotting, which makes backup and a lot of other things like super, super easy. But there are some customers that have asked us for local storage. And so with the i3 instance type, which we launched maybe 18 months ago, we introduced a Nitro Card specifically for instance storage. So the types of customers that are looking to do this kind of instance storage generally have their own durability mechanism, so they're maybe running a database that replicates data, or they're dealing with data that is really transient or isn't needed after a particular workload is done. Now, for a few generations of instance types, we did not have instance storage. So if you go back to the M1, the C1 generation, even up to the C3 generation of platforms, those always came with storage by default. And the reason for this is that networking and storage have evolved very differently. So if you go back to the C1 or M1 days, where you were still dealing with hard drives, those were the days of 1 gigabit networking. And if you look at what a hard disk could do in terms of throughput, or particularly multiple hard disks, you could actually achieve more throughput from those underlying hard drives than you could from the network. So it made sense to offer local storage on all instance types because it was just faster than you could achieve any other way. The introduction of 10 gig networking really changed this, because now all of a sudden the network is capable of meeting the performance of storage and often exceeding the performance of storage, which really became attractive to allow customers to really benefit from all of the other features of something like remote storage. The interesting thing that has changed, though, in the storage industry is the introduction of NVMe. So hard drives, historically, spinning hard drives, really haven't changed all that much in terms of their throughput capabilities over the years, because you're really limited by physics. There's only so fast you can spin that media before it's going to literally shatter and blow up. And so there's a ceiling there. There's only so much you can do. And when SSDs were first introduced as SATA SSDs, they largely used the same transports and protocols that spinning drives introduced. So even though the NAND was much more capable, the controller itself became a major bottleneck. With NVMe, they took that same NAND technology and they placed it directly on PCIe and really opened up the possibilities for much greater bandwidth, much lower latency. When we introduced the i3 instance type, the i3 instance type is capable of driving 16 gigabytes of throughput to the drives attached to it. That's equivalent to 128 gigabits of networking. And that's something that we introduced almost 2 years ago at this point. So obviously, we're now back in the world where local storage performance can actually far exceed what the network is capable of. And so this is really what led us to introduce this capability again, because now you can actually drive really tremendous performance from local storage. Now, there's one more property of the Nitro Card for instance storage that ends up being really important, but it's easy to miss, and that's drive monitoring. So one of the characteristics of NAND, so the great characteristic is they don't explode. So that's good, really important in a data center. But then the second not so great characteristic is that it wears out over time. So an individual cell of NAND has a finite number of writes before you just can't tell the difference between a 1 and a 0 anymore. And so modern drives actually have way more NAND than is presented to you, and they have a complex controller firmware that will actually decide dynamically where to place writes to evenly wear across the entire drive. Usually this works great. You can't tell it's happening really fast. But eventually that NAND is going to get worn out, and it's going to be harder and harder for the controller firmware to find NAND that isn't worn. And when that happens, you typically start taking really long pauses as the controller is trying to rearrange data and find places to put those new writes. And what you actually see in practice is usually the drive performance dropping off a cliff, a really significant degradation in performance. This is not what you want to happen in your application. And it's not something that most people expect to happen, so it's not an error condition they're going to design for in their application. This is one of the many things that we're monitoring for continuously in the Nitro Card for instance storage. We're making sure that all of the drives, we know what the state of the NAND wear is, and that we can proactively get those drives off of customer instances before it becomes a problem for customers. The unique characteristic of the Nitro system is that that same capability is available both for virtualized instances and bare metal instances, because it's all happening in hardware. We're not relying on a hypervisor to do this type of monitoring. Now, as I mentioned, we do a lot of monitoring in the platform to ensure that we're delivering a consistent performance experience. And that monitoring all has to happen somewhere. And the thing that really coordinates this is the Nitro Card controller. Whereas a traditional hypervisor is, you can think of as sort of a vertical application, where all of the various software is pulled together and is running on a single system with a shared fate. With the Nitro system, we actually have a lot of different components, and it's more of a network application. You can kind of think of it as almost a small cluster of compute resources. And so the Nitro Card controller is the brain that controls all of these different resources, makes sure they're all configured correctly, and presents a unified control API to the EC2 control plane. In addition to working with all of the different Nitro cards, the Nitro Card controller also interacts with the Nitro security chip and the Nitro hypervisor to coordinate the entire system as a whole, and ultimately implements the hardware root of trust. Now, I mentioned I wanted to talk a lot more about the Nitro security chip. The Nitro security chip is a custom microcontroller that we put on the system, and it sits in front of every bus that stores non-volatile storage. And it allows us to make sure that that storage is in the state we want it to be. It also is connected to the Nitro controller, and it's ultimately controlled via that mechanism, and it provides a simple hardware-based root of trust. But why do we even need this? Why is this a thing, and what does non-volatile storage in the system mean? In addition to all of the Nitro cards and the other components in the system, every modern computer is really composed of a bunch of different microcontrollers. Like I mentioned, the drive controllers are running complex software, but there's also software that is determining how fast to spin the fans to cool the system. There's a memory controller that's actually monitoring the memory bus and setting what the right frequency should be at any given point in time. And there's really this large variety of these devices. And all of these devices, they can range in complexity from something as simple as the equivalent of an Arduino to something as advanced as a Raspberry Pi, where you're running a full-blown Linux OS. In fact, chances are your systems today are running multiple operating systems and you don't even know it. All software can have bugs, and so all of these individual devices have to have a mechanism for upgrading their software. And that mechanism usually means there's a small bit of flash. Sometimes it's shared in a single bank. Sometimes there's multiple banks. But ultimately, there's always going to be a non-volatile storage somewhere in the system that is storing that embedded processor code. Now, the only way you typically interact with a server is through the operating system. So it stands to reason that if you as a user on a traditional server want to be able to apply those bug fixes, there has to be a path to write to that non-volatile storage from your x86 processor, in Windows or in Linux or something like that. And so people don't tend to think about this when they think about hypervisors, but one of the really important features of a hypervisor, besides protecting instances from each other and protecting instances from the host OS, is actually providing an isolation layer between all of these underlying hardware devices and the instances themselves, so that nothing you do in that instance can actually change what, say, the BMC firmware is, or something of that nature. Now, to understand why we had to build something here, I wanted to talk a little bit about what the rest of the industry does to provide this type of protection, because it'll really show why we felt like we had to do something different. So UEFI. UEFI is the modern version of firmware that is probably running in most of your systems today. Prior to UEFI, most servers and even laptops were running a legacy BIOS. And that BIOS is typically, to be honest with you, pretty horrendous. It's 16-bit. There's usually large portions of it that are 16-bit. And you might not know this, but GCC can actually compile 16-bit code. So in virtualized systems that have BIOSes, for a long time what we had to do is use a different compiler to build the BIOS than GCC, because GCC just doesn't support that. And the only open source compiler available is something called BCC, which only supports KNRC. Now, if you don't know what KNRC is, you're very lucky. It's a very old dialect of C that nobody knows anymore. But like this is how BIOSes are written, and it's just not where you want to be from an engineering standpoint. So UEFI is a breath of fresh air. It brings a modern development tools. It's a 64-bit environment. It uses modern practices. So overall, it's a really great thing, and it's a big advancement that's been made in the industry. That said, it's a lot of code. Depending on how you measure it, a UEFI build that you would put on a server could easily be tens of millions of lines of code. And it's 10 millions of lines of C code. Now, I've been an engineer for a pretty long time, and there's no way you'll convince me that there's no bugs in that much code. This is just the nature of what we do, right? But this is unavoidable. Like, this is an important thing for the industry to do overall. And so, like, UEFI has a role, and you have to play it. Anyway, how does UEFI solve this problem? It solves this problem through a mechanism called secure boot. The first observation is that UEFI runs on the general purpose processor. How does it know that it isn't already on a system that has been modified? How does it know that it's not been loaded by something where there's a BMC that's running code it shouldn't know? It doesn't know. It can't know. You start out in an untrusted state. And so then what UEFI does is it starts a signing procedure. So it'll walk through and it'll checksum every bit of thing that it can identify. And because UEFI is such a large system, obviously it has a bunch of modularity to it. And so you start out with early firmware, you move to the boot manager, you move to the various applications. You might ask yourself, what is a UEFI application? Well, the best one I've seen so far is Doom. Somebody ported Doom to run on top of UEFI. I'm not really sure why you need applications, but they're there. There's also UEFI drivers, and those are often coming from the cards themselves. So it's code that isn't even coming from the main BIOS vendor. Eventually, you'll sign all these things, and you'll get to the operating system. There's a whole bunch more steps, but I ran out of room, so this is all that you're going to see for today. You could easily do a 2-hour presentation on the way this works under the covers. But ultimately, what you end up with is you end up with a signature, a checksum, really. And that gets stored in another chip in the system that there's some physical tamper resistance to. And then remotely, you can query the system, and you can prove that that checksum is what was told to that chip, basically. Now, this is a system that is sound, like academically. If you look at it and you review it, lots of smart people have worked on it, and it is correct. However, what's important is what it's telling you. And what it's telling you is that as long as all of this software is functioning correctly, then you're running that software on the system. And like I said at the beginning, I just don't believe that all of this software and all of this complexity is going to be correct. So when we were thinking about how to support bare metal, the real question we asked ourselves is, how do we solve this problem in a way that is simple, that is easy to understand, that we all feel really confident in is going to be correct and not prone to error? And the answer we came up with was the Nitro security chip. The Nitro security chip is based on a very simple premise, and that premise is we don't actually care about what the rest of the industry cares about. So it's not necessary to allow the general purpose processors to update all of those embedded controllers. So what we do with the Nitro security chip is very simple. We don't allow the general purpose processor to write to those controllers. And instead, we provide ourselves a path to do those updates from the Nitro controller itself. Ultimately, this ends up being a very simple mechanism because it's a well-defined interface to talk to these individual devices. You can block writes once, and it applies to every single component in the system. I fundamentally believe that the best security is simple to explain. And by departing from the requirements and restrictions that general purpose systems have, we were able to really simplify the problem. The downside of this architecture is that we'll never be able to run a Windows graphical update utility to make a BMC software update. That's okay, I don't care. I like this a lot better. So when we have all of these ability to manage the system from outside of the general purpose processors, when it comes down to designing a hypervisor, we can actually remove almost all of the functionality. And that's what led to the Nitro Hypervisor. The Nitro Hypervisor is based on KVM, and KVM is a part of Linux. But it's not what you'd expect from a Linux installation. There is no systemd, there's no sys5 init, there's not even a busybox. There's just a small number of user space applications that were written specifically for this purpose. And all they really do is set up the right hardware bits, kick off the hypervisor, and then get out of the way. And the overall design goal for the Nitro Hypervisor is to be quiescent. And what we mean when we say quiescent is that we want to make sure that the hypervisor never executes on any core unless it's doing work on behalf of the instance that the instance requested. And with this architecture, it lets us make the Nitro Hypervisor nice, simple, easy to think about. I wanted to talk a little bit about what that means for you and what that means for an application. And I think the best way to do that is to show some data from a benchmark. Oops. Went a little too fast there. So earlier this year, I was working with a customer, and they wanted to bring a real-time workload into EC2. Now, real-time workloads are workloads that generally have a bunch of threads or some kind of applications, and there's some kind of event in the system. That event could be a timer, that event could be a network packet coming in, it could be a sensor from an arm with a laser that if you don't respond to it within a certain period of time, you'll blow a hole in the side of the wall or something like that. These are generally systems that cannot tolerate a latency in terms of responding to these types of events. And in this case, the customer had an application that has to process a network packet within 150 microseconds of receiving it, because the overall protocol that is used within their system expects the response within a fixed period of time where everything stops working. It's not good enough to get this 99% of the time. They needed it to be 100% of the time. And so within the world of hypervisors, real-time is kind of the Achilles heel. It is the thing that everybody kind of ignores and says, oh, it's not, you just use bare metal for that. And since we had i3 Metal, my first instinct as a hypervisor developer was, OK, we'll use bare metal, and we can satisfy your workload. But the customer actually pushed me to try C5. And so I said, sure, let's give it a try. Let's see what happens. And so we benchmarked C4, C5, and bare metal for this particular workload. Now, bare metal is the red line at the very bottom, and it behaves exactly the way I would expect bare metal to behave. It's pretty flat. It's pretty consistent. There's a very small spike at the very end that's in the very high percentiles. That's most likely systems management mode code. So even if you're on bare metal, the BIOS usually has a little hook that occasionally will run for a variety of reasons. And most likely, this was a small number of events where that code was running and had to wait to get the system CPU back. There are plenty of bare metal boxes where SMM mode code actually can cause really bad jitter. But we also control our biases. We build our own biases. And we've known about this problem for a long time, and we've made sure our systems don't have that characteristic. The yellow line is C4. And I actually think that this is a beautiful result for a hypervisor. I suspect if you took either your own local hypervisors or other cloud providers and you ran the same benchmark, you would not see a line that was this consistent. This is really hard to get right. And one of the ways we get this right on C4 is that we limit our control plane software to run on 10% of the cores on the platform. So as a customer, you're only getting to run on 90% of the available cores because we're trying to isolate the work we have to do from your application. And so, but even with that mechanism in place, you can see that we only meet the SLA at about the 70th percentile. We get close, but then when you get to the high percentiles, it shoots up to 750 microseconds. Again, I still think this is a great result, but doesn't meet the needs of their application. Now, what was surprising to me, but is obvious in retrospect, it's just that I've spent too many years doing this and I'm biased, even for the things I build. The blue line is C5, and what you see is that there's a very consistent small adder on top of bare metal. That's expected. There's more hardware involved in delivering an interrupt through a hypervisor. You have to go through the IOMMU. There's a few other things that come into play. So there is always going to be that small adder compared to bare metal. For most applications, it doesn't matter. It's a couple microseconds at best. And then the surprising part, though, is that you don't really see much of a difference in high percentile latency, even at the P100. The spike at P100 is very small and pretty close to bare metal, and it stays completely below the SLA line. This was a really exciting result to me, because what this result tells me is that applications that previously couldn't even consider being virtualized, we can bring into Nitro instances. And ultimately, as a developer, that's really what I'm trying to do, is to allow new workloads to be brought into EC2. I wanted to talk a little bit about how we're using Nitro in a number of the things that we've launched recently. As I mentioned earlier, this past year we've introduced a number of instance types with local storage, and this is the same local storage that is available in i3. So, and specifically in R5D is approximately half of the storage throughput as in i3. But every drive is effectively the same as what you'd get in i3 in terms of this throughput and capability. So this is not M1 and C1 era local storage. This is incredibly fast, high-performance local storage. Again, this is really optimized for customers that need scratch space or already are doing replicated storage. And it's very likely that moving forward, we'll have instant storage variants for most of the platforms that we build, as long as there's appropriate customer demand. We pre-announced i3 Metal, and we announced a preview of i3 Metal at last year's reInvent. But earlier this year, we launched as a GA product i3 Metal, and this is our first bare metal Nitro platform. This has been a super exciting platform for me because, again, it allows new workloads to be brought into EC2. The most interesting workload of all that this platform has enabled is VMware on AWS. That's been an amazing partnership. There's lots of exciting things that we've built as part of that offering. But the other thing that's been really interesting to me is to see other workloads that use virtualization that aren't what we would think of as traditional hypervisors. Something that this platform has become pretty popular for is Android streaming. Android emulators can take advantage of KVM for optimization, and we found a lot of customers running a bunch of Android sessions on a single i3 Metal instance to serve the content remotely to customers. And then another use case that is really dear to my heart that we'll talk to in a bit is what I like to call micro-VMs, which is a new way of thinking about serverless computing. Now, by simplifying the hypervisor and by removing a lot of the logic that needs to be part of the hypervisor, it's enabled us to make it much easier to replace the general purpose processor. And earlier this month, I believe, we launched a series of AMD-based instance types. There's been a lot of exciting things happening in this space. The EPYC processor is super interesting in terms of the number of cores that are available in it. And this ultimately allows us to deliver cost savings to customers. So if you have a workload that requires a certain level of performance that that doesn't require an Intel-based processor, there's an opportunity here to lower costs in a very compatible and easy-to-use way. Now, an instance type we launched earlier this week that also has been really exciting is the C5N instance type. And this is actually using the latest generation of Nitro processor and is kind of a preview of what's to come in the Nitro space. And so this is a platform that allows for up to 100 gigabits of networking throughput. And the other thing that's really kind of interesting about this platform is we've really focused on optimizing latency in this new generation of Nitro chip. So if you have a workload that is doing HPC or distributed machine learning where there's a lot of inter-node communication, you can see really tremendous performance improvements on this platform. The other thing that this really enables is really high throughputs to S3. A lot of applications actually are compute intensive, but they need to pull in a lot of data to do that compute. And the data ingestion or the data push cycles of those workloads end up dominating the overall time. With C5N, you can significantly cut down the amount of time it takes to pull large data sets from S3 to perform compute due to the much, much higher throughput available on this platform. Now, I talked a bit about the Nitro Hypervisor allowing us to introduce new CPU architectures more easily. And one of the things I'm incredibly excited about that we announced as part of this week is the A1 instance type. Now, the A1 instance type uses the AWS Graviton processor, which is based on ARM and is in the same family of processors that we use on all of the Nitro Cards themselves. So it's actually a platform that I, as an engineer, have been spending most of my time developing on. And I can tell you firsthand that you can build amazing things for this platform. You can build software, if you take advantage of all of the right things, that drives really high I/O performance with very less compute than you would typically expect. Now, even without completely redesigning your application to take advantage of this architecture, we found that for certain workloads, particularly scale-out web applications, you can already get a 45% cost savings moving that workload largely unchanged to this platform. And as part of the launch, we already support Amazon Linux, RHEL, and Ubuntu. So you largely can pick up and do things just the way you've always been doing them. I am really excited about this platform and particularly working with customers to build their applications to really take advantage of its unique capabilities. Now, we've talked a lot about instances and virtual machines, which makes sense because I'm a virtualization guy, so it's really what I like talking about. But a lot of our customers today are using containers or some form of serverless to run their workloads. In fact, I would go as far as to saying that most new applications that are being delivered as containers or some kind of serverless workload like AWS Lambda. And we started asking ourselves within the last year, can we apply the same lessons learned in Nitro to the serverless space? And what we came up with was Firecracker, which is a project that we announced earlier this week. And what Firecracker attempts to do is bridge the gap between virtualization and serverless computing. So, it's a small industry, and I know a lot of the folks that work on containers, and there's always been a bit of a healthy rivalry between containers and hypervisors. And really, that's because there's a trade-off, and that historic trade-off has been security and isolation and consistency versus speed, flexibility, and performance. And so a lot of us have talked about over the years that, hey, wouldn't it be great if we could bring the two together and come up with a common technology that gave you the same kind of agility and speed of containers or function virtualization, but offered the kind of performance isolation and security guarantees that come from using virtualization. And this is our answer to that. This is our answer to how we provide the best of both worlds. When designing something like this, security is of the utmost importance, and that was the primary thing that we focused on. And unsurprisingly, one of the ways that I think about security is simplicity. So Firecracker only contains the things that are necessary for running serverless workloads, and nothing else. The other thing is speed. If you want to run a Lambda function that is only going to execute for 500 milliseconds, you don't want to wait 10 seconds for that function to start. That's extremely wasteful. If you're going to run Windows, and Windows is going to apply a lot of software updates during boot, and that's going to take 15 minutes, you probably don't care if it takes 10 seconds to start up. It's a different world with different trade-offs. The other big trade-off is scale and efficiency. In a dense hypervisor deployment, it's typical to see tens to maybe 100 at the max, maybe a couple hundred virtual machines on a single physical server. I would say if you're running 200 virtual machines on a server, you're doing a pretty good job. You've got a pretty good scalable system. However, today, it's not uncommon to find commodity servers with upwards of a terabyte of memory, and a Lambda function can run a footprint as small as 128 megabytes. 100 is not even close to the scale needed for these types of workloads. So Firecracker also focuses on minimal footprint and the ability to scale to very large numbers. Earlier this week, I showed a demo of running 4,000 Firecracker VMs. They all executed within a minute. And the overhead of the runtime within Firecracker is under 5 megabytes per image. Now, this is a really emerging space, and there's a lot of community activity. And so we immediately from the beginning thought that the thing that was going to be needed to make this successful is to do it as an open source project. And I'm very happy to say that as part of announcing Firecracker, we also released this as an open source project on GitHub. We announced this on Monday in Peter's keynote, and I was thrilled to wake up the next day and see a bunch of pull requests already sent for Firecracker. And so it's been really great to see the response. I'm really excited. I've already had a number of great conversations with the community. If you saw me sitting on my phone before this talk, I was actually reading Twitter about Firecracker and seeing the various conversations. So really exciting space, and I'm really excited to see what the community builds with us. The other thing I'll mention here is that Firecracker, because security was so important, we actually looked at tooling for making sure we could have stronger security guarantees than you would typically have in a hypervisor. We've spent a lot of time focusing on ways to ensure that we were very safe in terms of memory usage in the Nitro system. We apply a lot of techniques like formal verification, penetration testing, coding guidelines, things like that. But what's interesting about Rust is that Rust is really the first language to appear that has strong memory safety properties built into the language enforced by the compiler without the performance trade-offs of introducing garbage collection. For something like Firecracker, where we're measuring runtime at the P100 in milliseconds, having a multi-millisecond garbage collection pause isn't acceptable. And so any kind of garbage collected language is just not appropriate for this type of application. And it's been really amazing to get to work with this relatively new language and really see how well it solves this problem. So the other thing to call out about Firecracker is that even though we're using this today in Lambda and Fargate, it's still very, very early days. Open source is near and dear to my heart. I firmly believe that the best way to build an open source community is to have something that's useful from day one, but still has a lot of work to do, and that's absolutely where we are with Firecracker. So I'm really looking forward to continuing to work with the community to turn this into something that all of our customers can just take and run and do amazing things with. So as I mentioned at the start, I wanted to talk a little bit about what's coming next. And last year, I did a similar slide, and I made a statement that our roadmap really comes on the feedback from customers, just like you. 90% or more of our roadmap comes directly from our customers. And one of the things that our customers have been asking us for a really long time is to be able to have EC2 capacity closer to them physically. Many times they have legacy data centers running potentially a legacy database or some kind of workload that they really need to have super low latency, but they want all of the experiences of using EC2 in AWS, They don't want to deal with having to think about wear leveling of drives or any of the other things that we do on behalf of customers. The problem is, while our customers have been giving us that feedback for a long time, we didn't know how to solve the problem. So obviously, the hypervisor is by far the most important part of cloud. Being a hypervisor developer, that's my worldview, and that's, of course, the right answer. But the reality is, if I gave you a Nitro server today, and I let you take it home, it would be a really expensive paperweight. There's not much you could do with it. Because while hypervisors are super cool and are obviously the best thing to work on, it takes a lot of control plane services to actually do things with that data, to actually predict when the drive is going to wear out. All I know is, how many writes have happened. I don't know when it's going to fail or things like that. There are literally hundreds of services that all play a role in making EC2 be the experience that our customers have. And all of those services are built to be multiple AZs for high availability. They have dashboards, they have canaries, they get deployed to on a regular basis. And there's really just no way to take all of that makes an EC2 instance really what it is and shrink it down into a little stack that runs on 1 or 2 virtual machines. It just isn't possible. You can make something that kind of, sort of feels like it, but it'll never will be it. There will always be an uncanny valley of experience. However, we had a bit of an epiphany this year. And we realized that if we took Nitro, and we took its design of being very passive and very simplified, and we combined it with the same underlying technology that powers Private Link, we could take individual Nitro servers and expose them back to our control plane and really give you the best of both worlds, where you could have the same physical hardware that we use in our data centers, running the same software that we use in all of our data centers, wherever you needed that hardware to be, but then still get the benefits of the AWS control plane and all of the things we do to ensure that all of those instances are happy and healthy. This is a really, really exciting project. It is really early. We wanted to let customers know what was coming, which is why we pre-announced it. But I think this is going to be a super interesting space. I'm really excited about it, and I'm really excited to see what customers do with it. Thank you all very much. If anybody has any questions, there's a mic over here, and we have about 10 minutes to take questions.
I had a question. Recently, you announced the elastic fiber adapter. So how does the elastic fiber adapter intersect with the Nitro hypervisor?
Yeah, thank you for asking that question. I did one of these sessions earlier today, and I talked about the elastic fabric adapter, and I forgot to in this deck. So you saved me from getting into trouble. So the elastic fabric adapter is part of the Nitro Card for VPC. It's another personality that we can use to present a networking interface to our customer. The elastic fabric adapter provides, instead of providing a traditional Ethernet interface to guests, it provides a RDMA interface or an RDMA-like interface to the guest. What this allows is for you to use applications that are built for things like libfabric or OpenMPI to be brought into EC2 and to largely just work. The other big benefit of the elastic fabric adapter is that it is strongly optimized for latency. And so you can get the lowest possible latency between 2 instances by using EFA. The other really exciting thing about EFA is that it's built on a networking primitive that we built called SRD. And SRD allows you to have a lossless experience of RDMA in an elastic way. And so if you've used RDMA before, one of the things you might know is that typically it requires very special connectivity fabrics. And those fabrics simply don't scale. You can't build clusters of thousands of nodes. It just doesn't work. That's not how the technology works. One of the really exciting things about EFA is that it actually scales elastically the way that our customers have come to expect.
I had a question about the simplification of the hypervisor with Nitro.
Okay.
You mentioned that the hardware enables a simplification. I was wondering in what ways, what are the major things that are simplified in the Nitro Hypervisor. And also, I was wondering about the just how lightweight can it be made in terms of like memory footprint, because nothing is zero memory footprint.
Sure.
And memory only comes in certain quantums of capacity. So typically powers of 2. So when you see an instance like on an A1 instance, it's 32 gigabytes of RAM.
Yep.
Is the hypervisor hiding in there somewhere, or is it taking up 32? So
I'll start off by answering the first question, which is, what's an example of simplification with the Nitro Hypervisor? So a good example of that is software updates. Think about what's involved in updating, let's just say a typical Ubuntu Linux installation, right? If you use Ubuntu, I'm sure you've run into a circumstance where you've tried to do an apt-get update or upgrade, and something doesn't work quite correctly, and you end up having to do a dpackage-f or some other like terrible thing. There's a lot of complexity there. A lot of it is necessary complexity because of the design of the system. The Nitro Hypervisor can't do a software upgrade. The Nitro Hypervisor is always delivered from one of the Nitro Cards as an in-memory image, and there's no need to have a mechanism to update because we can just change whenever we need to what that image is. So this is just one of many, many mechanisms where it's just simply not needed anymore in an architecture like the Nitro Hypervisor. I think I forget what the second part of that question was. It was?
The question is just like how small can you shrink it?
How small can you get it? You can actually tell. You can check. So when we say that an R5 24x large instance type has 768 gigs of memory, that is the amount of memory in the underlying physical system. And so what we do is we reserve some of the memory through a mechanism called the E820 tables, which goes way back to legacy BIOS, but is still present even with UEFI. And this is a mechanism that's commonly used by firmware. I mentioned SMM as a management mode. This is a common mechanism for reserving memory for things like that. And so the goal we set for ourselves is to make sure that the Nitro Hypervisor doesn't have noticeable overhead compared to what you would normally expect to see from system firmware. And we fit within that mechanism today. But you can actually just go and, if you look at like the Linux boot up prompt and it shows the E820 tables, you can actually even see the memory that's being used by the Nitro Hypervisor.
With the 100 gig instances, is that only the network traffic, or what about the storage network traffic, or is it is it to be shared between multiple things, or is it separate physical connection for storage and network?
Yeah, so like I mentioned, the Nitro Card for EBC is a separate card than what we use for EBS. And for C5N, it's the first generation of the new 100 gig Nitro Card. And today that's only available for networking. But as you can probably imagine, we're looking at using that same technology to accelerate other types of I/O, including storage. So I'm sure you'll see more from us there at some time in the future.
Just once in a while, I wish I had a TPM chip that was attached to an EC2 instance, and I was just your Nitro security chip reminded me of that.
Yeah.
I'm curious if that's a common request. Like I know in a cloud architecture, you have your KMS or whatever that's external to the system, but is that something that people ask for, and is that going to happen someday?
Yeah. One of the things I like about instances is that I don't have a TPM chip. A lot of customers have asked for TPM chips. Usually we have conversations about what you'd actually use it for. One of the things that's different about an instance compared to a bare metal system is that there is no way of changing firmware in an instance. So that whole mechanism to establish a secure boot, because you're starting from an untrusted state and you have to establish a secure state. But every single EC2 instance has a mutable firmware for the guest and starts from a secure state at the very startup day. So a lot of the traditional use cases for using TPMs really just don't apply. I know there's software out there that wants to use a TPM, that really wants to have that interface. We're certainly open to building something like that. We're really just looking for customer feedback about what they would do and what are the right use cases. But as far as I'm concerned, the biggest use case for a TPM is to support legacy workloads that expect it to be there, but I don't actually think it provides a lot of value in a cloud-native application. But always open to feedback there, and happy to build it too.
Yeah, for network latency, you just told us that your network latency is very low. So my question is, do you directly pass through your ENA to the guest?
Yes. When you send a packet from an EC2 instance on Nitro, or you write to a block device within a Nitro instance, the hypervisor is not involved in that in any way, shape, or form. When you do an LSPCI within that instance, you are seeing direct attached PCI devices. And the only thing that the general purpose processor is involved in is the IOMMU and the kind of mechanisms necessary to do that pass-through. But all of the I/O devices within a Nitro system are pass-through.
So if you direct pass through the ENA device to the guest, you just told me that in the future you will support the container, a lot of container in your system. So do you have enough device?
Right. So the question was, what do you do about networking for containers, right? Yep. This is actually one of the reasons why I'm so excited to have Firecracker as an open source project. That's actually one of the conversations I was having earlier today is about what's the right way of doing networking for containers. I could talk for a long time about this. There's a lot of interesting stuff happening in the container space. We announced today a container networking service called AWS Service Mesh, I believe is what the name was, which provides Envoy-based mesh networking. It really kind of, you can almost think of it like it's an L7 or layer 7 version of VPC. It's really exciting stuff. So yeah, we definitely want to provide the highest performance experience to containers, but I also think that container networking is in a different world today than what instance networking is. It's less about Ethernet and IP protocols and a lot more about RPCs, REST interfaces, HTTP, things like that. So it's a super interesting space, and I'm super excited to explore it with the broader community.
Okay, I have another question. You download many of the components to the card, right? So do you still, in cloud computing, we still need some component, for example, the system monitor in the main board, right? So if you still use this, you still leave this component in the main board, how can you provide CPU stable?
Right. So the question was, there are components that are required to bring the system up, like the baseband controller. Like, how do you actually make that work if you need to measure that before? The answer is very carefully, and it was a hard problem, but we figured it out. So yeah, there's a lot of details there, more details than I could go into in the less than a minute we have. But maybe one day we'll publish more information about that. So I don't have any more specifics than that today.
So my real question is that in the figure you show me that for C5 instance, the CPU queues, for example, the jitter is very stable. And if this component work, and how can you steal the CPU times from the system?
Yeah, so the question was, like, how do you get really low jitter if you have to do work? Yeah. And the answer is you have to move work off to other purpose-built hardware in the system and not do it on the general
exactly.
processors. Yeah. I have time for one more question, so maybe the person behind you.
How does Firecracker protect it from Spectre and Spectre-like issues,
That's a great question, and this is one of the reasons why I think security is so important in the container space. So we actually have a document in the Firecracker repository with a suggested configuration for production instances that will have all the necessary mitigations for all of the side channel vulnerabilities that have been discovered over the last 18 months. This is one of those areas where turning that into something that's easy to do and easy to consume is work that we're going to have to do with the community over time. The information's there in the repository, but it is a fair bit of tuning. Getting a really strong environment for multi-tenancy is actually a really hard problem, and so it's one of the things we're really interested to work with the broader community on. So that's all the time I had. Thank you all very much.